Sears because about a year ago we had the most fabulous tour of ThinkBox. Both a presentation about its origin and how it came to be, this amazing makerspace that they have on its campus, and this gentleman behind me and his bride were the people responsible for creating this. What's neat about it is not only is it an incubator for new ideas, entrepreneurial ideas, like a company called Cleaner, and Grace is here from Cleaner, and we've had her as a speaker. They make a thing that actually captures the microplastics from your washer. And that was technology that was basically incubated and developed at ThinkBox. The ThinkBox is also open to the general public. Anybody can walk in and they could take advantage of 3D printers and all of the materials they have there. So it's incredibly forward-thinking, community-oriented, and a place where true entrepreneurial ideas can come together, particularly ones that relate to engineering. Anyway, we had this program with Larry, and Larry was brilliant, as he always is. And then we said, we really want to get you involved in Ecophilia. And he said, well, pardon. You know, I really like and respect what you guys are doing, but there's an awful lot of nature stuff. Couldn't you do more engineering things? And as I recall, I was in the Sears' kitchen, and, well, Larry, would you like to do a program? And he came up with this idea, well, I'm fascinated with failure. And so that's what we're going to hear today. But I'm going to go quickly through Larry's bio, because it's amazing. Larry Sears is the founder of Hexagram Incorporated, which began as a design and build electronics company, and ultimately evolved into one of the leading providers of wireless systems for automatically reading utility meters, something which is obviously of universal necessity and appeal. He is now part of Aclara Technologies, a division of Hubble Incorporated. He's also the founder of ThinkBox, Case Western Reserve's 50,000 square foot technology innovation center, featuring state-of-the-art fabrication and manufacturing equipment, as well as support for entrepreneurs, faculty, and students. ThinkBox is the country's largest open access, university-based invention and commercialization facility. Mr. Sears holds or co-holds over 20 patents relating to a variety of industrial, commercial, and communication products. Have you retired?
I retired from the company, 20 years ago, but then I was teaching at Case until the past year.
And you retired from that?
Mostly, yes, right, mostly.
So
until I got shanghaied into this.
Well, so I'm over at the Sears' house, and Larry invites me to go down to see his shop in the lower level. And it's all this metalworking shop, and he says, Ernie, real men work in metal. None of this woodworking stuff. Anyway, and it was a tinkerer's paradise. There was just more cool stuff. So this is a brilliant man, a dear friend, and we're delighted to have him speaking about to air his human identity. Larry Sears.
Yeah, thank you for that introduction, Harvey. It was probably in error itself. So, is this working? Testing?
That is, but this is the one that you're using.
Oh, okay. Oh,
for the PA.
Oh, I thought this was the one.
No, that's
Yeah,
going,
all
that's
right.
going
See, communication errors. That's how things. But I have to get closer to this, so let's move it a little bit that way. All right. Okay.
Larry, if you want, this is a wireless mic. You can just grab it.
Yeah. Oh, okay. Yeah. There we are. Different keyboards. I've never done a PowerPoint this way, so we'll see how it goes. I hope you've all read that. That's the introduction, so I don't have to repeat it. Can't hear it?
No,
This one?
This is.
Yeah. How's that? Oh. Okay. All right. Okay.
It's insensitive.
Yeah, it's not. Okay. So people, have studied and thought about failure in engineering, not forever, but it started probably in World War II when everybody was in a hurry to bring technology to war. Sounds pretty current. And they, of course, had to then feed back and figure out what went wrong. So after that, you had people in the 50s looking at operations research, and they started looking into failures and analyzing it and cataloging it. And then the sociologists and the other people started thinking about it, philosophers and anybody involved with neurology and what's going on in people and whistleblowers and all that. So it's a very, very interesting topic. If you've become addicted to the YouTube videos on tragedies and airline crashes and stuff, you'll understand why, why you can really, it's a very, very complicated topic. I won't even talk about medical errors, because that's a whole other area that brings to mind all kinds of, obviously, concerns and, tragic incidents that we've probably all heard about. But I'm going to be talking about incidents and accidents. That's how a couple commentators have referred to engineering. Incidents are things that don't really bother anybody. You buy something and it's a piece of junk, or you buy it and it breaks. And it's common and it's annoying, but it's not really terrible. And so that's why we call those incidents, because they don't have consequential problems or people don't get hurt typically. Accidents are more serious. Accidents are things like airplanes crashing or bridges falling down or a bunch of other frightening things you can think about. So spend a little bit more time talking about those, and I hope that some of these examples and topics will bring up some questions, and we'll try to do that as I go along. So, incidents. All right, we always come back to the root causes. How did these things happen? And of course, that is the challenge. So, I'm gonna have to lean down on this. All right, so let's see if this works. Oh, it worked. Okay. So, incidental failures. I'm gonna hold this. There we go. All right, I should know wireless. So, this was one of my favorites. I didn't do this. I didn't make this thing. It was a radio or some gadget, and it came with a line cord all hanked up, with a plug at the end. Well, they built a device, and then they attached the line cord, and then they shipped them, not realizing that you could never untangle the line cord, because you had to pass the device, the radio or whatever, through the hank. So the line cord was permanently there, and nobody could use the product. I mean, that was a catastrophe. But it just goes to show you that, these problems can sneak up on you. When we made things, we would always take it to the end. You would actually put it in the box, ship it back and forth to your neighbor 10 times, and, make sure it survived. And if they had done that with this device, they realized that they had shipped, something that was dead on arrival. The first thing that I made when I was in a storefront on Murray Hill, trying to get in the electronics business, I was able to make this little gadget for Monsanto. I don't think it's around anymore. And I don't remember what it was for, but it was some kind of an electronic control. It was a timer. And I probably made 100 of them, which was very exciting, and it looked nice. And then they all started going bad immediately. Interestingly enough, the ones in Alaska worked. The ones in Florida never did. They failed immediately. So does anybody here figure out what the problem was? Well, humidity is good, salt water, salt spray or something like that, but that's only near the coast. No, it was lightning. If you want to test something for lightning, send it to Florida. But for those geeks in the field here, and I think we have a couple, I gave you the schematic. What happened was that this was designed like you would learn in your first year circus class, and it should have worked. And you look at it on paper, and indeed it would work just well. In fact, it worked just fine until you sent it to Florida. And the problem was that you don't learn to take into account lightning strikes and transients. And lightning is, of course, a pretty rough thing. So I designed this thing that it'll run on 120 volts that comes out of the line, and then a 6,000 volt transient comes along. So that little 5-cent part right at the beginning there, that diode was rated at 400 volts, and I figured, well, that's plenty. But in the reverse direction, it just goes up in smoke instantly. So that was embarrassing, but there was a lesson there. I never made that mistake again, and it was good fodder for teaching electronics, obviously. But you know, I moved on from there, fortunately. Whoops, sorry, I gotta do my trick here. I learned this is a very good aspect of PowerPoint, to link things. All right, so that was design and manufacturing. Then we come to what else can go wrong is product testing. Now, I was called into this more like a consultant. Eaton Corporation at the time was making HVAC equipment, and one of the things they made was a humidifier for a house. And this is a box that sprays water into your heating vent down the basement, and it humidifies the air. And they were manufacturing this thing, and I got called into this, you know, factory, and these things were on the assembly line ready to go, and they had shipped some, and they didn't work, and they didn't know why. I mean, it just was driving them crazy. So I looked into it, and turns out that they had done something very professional and very common. They had copied a circuit out of that manual that you see down there at the bottom, and they thought that it would work because it was a General Electric manual and they know what they're doing. The problem is that it worked in the lab when the humidistat, which was sort of like, you know, a thermostat for humidity, which would be mounted on the wall of your house, it was 50 or 100 feet away from that box in the basement, and the resistance of the wire was enough to make it malfunction. So, and they said, well, we're going to sue General Electric. And I said, well, good luck with that. You know, I mean, these manuals are made for, you know, hobbyists and things like that. So, but that was interesting. They probably learned a lot more than I did, but things happen, and even the largest companies can make mistakes. For instructions and operation information, this has become sort of an internet meme about the translations of imported equipment, and you try to read the manuals, and it's entertaining. And this is just one example. And there was actually a book written on nothing more than mistranslations from a variety of languages. So, but just another example of what happens when you have these little products. We don't need examples of misapplication or misuse. There was a rumor going around years ago that landscapers were taking rotary lawnmowers and lifting them up and using them to cut hedges. And obviously the insurance companies were going crazy. I don't know if that was actually true, but it went around for a while. And then, of course, you know, you buy a tool and you don't sharpen it, or you just use it wrong. So that's what caused these little incidents. Here's one of my favorites. I'll put this down. This drives me crazy. All right, so this is a bottle of aspirin that hasn't been used. This crazy piece of paper they put here, you cannot get those off. And every time you open a bottle, I say to myself, didn't the owner of this company ever buy aspirin and try the thing that his company makes? I mean, you need a machete to get it off, you know, or dynamite or something. And I just don't understand that. And then they came along with the ones that have a little tab, and it says pull here, and that's even worse because, you know, the tab tears off and it doesn't do anything. So this is an example of an incident, all right, and it's frustrating and it's aggravating. And I wonder, didn't anybody try it, you know, before they made it? So anyway, all right. So now we get into accidents. This is the serious, you know, tragic stuff. So we go back and we look at, the things that can go wrong, and let's go to design, you know, the fundamental sort of genesis. Pardon? The mic is also direction. Okay. Whoop. Like that? Ah, very good. Okay. Thank you. So, you know, we're talking about the system or project design, something big. It's a bridge. It involves all kinds of engineering. It's very, very complicated. And certainly things can go wrong, and they can be little things or they can be big things. So a couple of satellites here. Got to get this straight. The Mars Climate Orbiter was famous. That happened fairly recently, where there were two contractors, one working in metric and one working in English. And you can imagine what happened. So the numbers got messed up in transcribing them and moving the drawings over, and a $500 million satellite crashed because some intern didn't realize what was going on. The Mariner 1 was a long time ago, and this thing was landing, and it had a parachute to help, but of course in the Martian atmosphere it didn't help much, so they had retro rockets, which were supporting it as it landed, and it had legs that had to open up, because of course they have to close everything up to get it to fit in the nose cone. So it comes down, the legs open up, and the satellite decided it was already on the surface. So it turned off the rockets, and the thing crashed. What happened was they had some kind of a sensor, and I'd never figured out what kind it was, but maybe it was just a switch on one of the legs, or maybe it was some kind of velocity sensor or something. But the opening of the legs was enough of a shock that it fooled the sensor into thinking it was on the ground, and that was the end of it, because it turned off the rockets and the thing crashed. So that's where testing comes in. I mean, maybe you can't calculate something like that because you don't know exactly what the atmosphere is, and there could be variation of the speed that is coming down. But my goodness, you should be able to test it, and look for that type of event. So that was a pretty classic. And of course, when you think about on television, when probably years ago, you see news story after news story of rockets blowing up. It took them a while to get it right. Now they'll, like this latest, I forget what it's called, the one that has the astronauts, and they just tested it a couple of times. I wouldn't get in that thing, so. But it seems like they always have leaks. I mean, your house doesn't leak all the time. Yet these incredible rockets are always leaking. I just never understood that. So. Okay, so manufacturing, assembly, or installation mistakes. Does everybody remember the Hyatt walkway collapse? Several hundred people died. And what happened was that if you look over here, at every one of these iron bars, they had a box beam going under the walkway, and that supported it, as you can see here. And originally, by the way, this was an example of sort of consecutive errors. Originally, they had one steel bar, here's one steel bar, supporting both walkways. And the bar went through the upper box beam, and the box beam is going the width of the walkway. And then there was a nut and a washer here, which supported this box beam, but the metal rod continued to support the second box beam and the second walkway. Well, if you stare at this, you can realize there's no way to put this nut on this rod because it's not threaded. You can't slide the nut all the way up and then put the other box beam on it. You couldn't assemble it. And they realized that, so they came up with this very clever idea. The one rod would come down, and it would have a washer and a nut here. And the second rod would come down, and it would have its own nut and washer here. And that solved the problem, except that in this configuration, the force on this nut is the weight of one walkway, and the force on this nut, trying to pull it off, is the weight of the second walkway. In this configuration, the force on this nut is one walkway, but the force on this nut is two walkways. Now, first of all, you say to yourself, a safety factor of 2 is not very tough. I mean, a safety factor of 3, would probably be used for a lot of situations like this, but obviously they didn't, and a force of 2 times was too much. But when you think about it, that's really risky because you could have twice as many people on the walkway as you thought, or they could have had a big dinner and weighed a lot more. So I don't know, a safety factor of 2 is scary.
You know about hip hop, right?
Yeah, forget about dancing, and that's happened on bridges too. The Millennium Bridge in London, they had to shut for a couple of years while they fixed it. And there was another problem related to the size of the washer. All right, so if you look how the beam fell apart, you see how the bolt and nut pulled through. Somewhere I heard that the washer was too small too. So again, you've got all these problems, and it's easy to look at them and figure out what went wrong now, but, not when you're under financial constraints and, somebody's yelling at you and all that. Let me go back here. Improper knowledge or modeling. Modeling is really important because you can't always guess what your environment's going to be. And a good example is a concrete dam. You realize, of course, that a concrete dam is an arch lying on its side. And if you press on the top of an arch, the legs of the arch try to expand, but something is preventing that from happening. A good example is a cathedral, where you have flying buttresses on either side. And the purpose of the flying buttresses is to prevent the legs of the arch opening out. Well, the same thing is happening here, except, the arch is lying flat, but if you look at the top picture, those walls are preventing the arch from flattening. And the load, the water, is on the other side. So it'll work. Concrete loves to be in compression as long as the walls are there. Well, the walls maybe aren't going to be there because obviously you have earthquakes, but just, they have geologists crawling around and drilling holes and stuff like that. But many times they just don't know what is the bedrock underneath the wall and all this. So the ability to model something in an effort to predict what's going on it can be a real challenge. And of course you have to model, in this case, the walls, but if you're building a refinery, you have to model your refinery too and what's going to happen there. So that is a big part. And then this is the incident. We got to go back to the accident. Unintended feedback loops. Okay, and so I'll mention another one of my experience. This is the Bingham building, which is on the campus here. And there was this thing years ago before you had big computers and finite element analysis. If you wanted to understand stresses, you're pulling on something, is it going to break? That is very, very clever, although rather intricate or involved method of modeling these things. You would take a piece of flat plastic, a 1/4 inch thick of acrylic, and it had this interesting characteristics that if you stressed it and looked at it through the right arrangement of polarized light, you see beautiful little fringes like that. And the spacing of the fringes indicates the stress. So if the fringes are real close together, like over here we have a beam supported on two sides with pressure in the middle, you can see the pressure is highest in the middle. That's pretty easy to figure out, but if it's a complicated shape, with holes or something, this is a very handy analysis. For example, here's two teeth of a gear rubbing, and you can see the stresses are very high at the point of contact. And this is a cantilever. So the way this worked is you had a light source and you had your acrylic model, and then you had a camera or some gadget over there looking at the polarized light coming out. The one requirement, though, is that in order to match index of refraction, you had to put this acrylic model in basically a fish tank, an aquarium of a special liquid that matched the index of refraction. So there was an aquarium on this thing, like this big, and it was sitting in the way, and the model was inside. But we had to get, or the graduate student I was working for, had to get this special oil, which turned out to be really expensive, because how many people need it, So he decided to make his own, and he mixed glycerin and who knows what, olive oil, whatever, and he got it to work. He did his experiment, and I made my gadget to measure those fringes and read out the spacing, and then everybody went home for the weekend, and then it blew up. It exploded. And it was an exothermic reaction between this mystery oil and the copper angle irons that were part of the aquarium. Now, who would figure that out, I mean, it sat there for a month, and then maybe it was August, the temperature got a little higher, kicked off the exothermic reaction, and it went so fast, it just destroyed everything in that room. I mean, I opened the door, everything was smoking and covered with black soot, which is the oil, and I just went home. So that was, but he got his degree, and it was I don't know, they just, I imagine they just threw everything out in this room. It was disgusting. So that was the idea behind a feedback loop that you don't realize is there. Typically, something that regenerates and causes more problem. Close coupling. These books that I mentioned, they're big on close coupling. Okay. The idea is that if you have a process where things are closely related, they can be too closely related. And a very simple example would be, say you have a fire alarm. Okay, well, a fire starts and the fire or the explosion turns off the power supply to the alarm. So there is no alarm. So that's an example of something that is closely coupled without redundancy. Or, maybe you have a temperature sensor or something, and the thing that is powering the temperature sensor, that breaks, and then you can no longer measure the temperature because, again, those two things are related. So you want to have redundancy and all kinds of things. The godfather of close coupling and lack of redundancy is 3 Mile Island. 3 Mile Island was obviously an incredible experience, let's put it that way, and it really changed the way power plants were operated. But the way it worked, and again, these are all sequential events with no break. We call that now a circuit breaker, something that breaks the idea of these events happening one after another. But what happened was there was a failure in the non-nuclear part, just basically the steam turbine that uses what amounted to water that had been you have dirty water in the reactor. Then there's a heat exchanger, which transfers the heat to clean water, and the clean water, goes out into the world and runs the turbine and stuff. But the turbine broke down, something happened, or there was a leak, so they had to turn that off. Well, when that happens, you sort of have this reactor sitting there churning, putting out a tremendous amount of energy, but no place for it to go, so automatically it shut down, and it should, because that's what it has to do, because it has no place for the energy to go. So if you do that, though, you have residually a stored heat in the reactor, and things start heating up and boiling again. So what do? Well, you have to vent it. You have to vent the pressure in this reactor. And so the release valve opened, that's good, but it's stuck open and it can never be closed again. So all the steam and water that was cooling the reactor started going out this pipe. Okay? And obviously then the big problem is you're no longer cooling the reactor. Then everything escalated here because they couldn't measure the temperature in the reactor. Okay? Why? Well, they measured the water temperature, but there wasn't any more water. That actually happened to me on a car once. I was driving along, and just strange things were happening, and what happened was the temperature gauge said everything was fine, but there wasn't any water in the car. So I don't know how they do it now, but that was a problem. And that was in Kentucky someplace. But anyway, in this particular case, several things happened. One was that the range of the temperature device wasn't enough it got so hot, the needles in the readout devices were pinned. They couldn't go any higher. They didn't know what was going on. And then in one case, somebody had a handwritten label for some other purpose. Basically, it was a tag that said, this will be fixed on Thursday or something. And that tag was covering the one thing they had to look at. So it was just, and I'll talk about this later on, but it was absolutely terrible. But they did have these pumps, of course, but then the pumps broke. All right, the pumps had bubbles in the coolant pumps, and they had to be shut down. And then they just had to let this thing vent, and then of course there was no water to heat the core because they had vented it all out, and that's why the core was exposed and melted down. So that's what happened to 3 Mile Island, and it's just you read, there's obviously books written about it, and it's just horrible. They learned a lot from that. Unexpected catalysts or instability. Okay. Oops, sorry. We'll get back to that. So in other words, a lot of things are tricky. Well, even like that exothermic reaction I mentioned, that happens a lot in refineries and power plants that are always in Texas or Louisiana and are always blowing up. Things just get out of control. I mean, so many things are linked. I'll talk about some of those, but 3 Mile Island had something that may or may not have happened, and nobody ever expected it, and now they're not even sure if it happened. And that's the infamous hydrogen bubble. Over here they talk about it, ye famous hydrogen bubble. So there was a reaction with zirconium or something, and they said it shouldn't happen, but maybe it did happen. It turns out that it never would have exploded anyways because there wasn't enough oxygen. So it wasn't a stoichiometric mixture, and it just, if it was there, it just sort of sat there. But again, that's an example of something that the modeling broke down. They really didn't know what would happen. Another very interesting one is, I'm sure that everybody's heard of nitroglycerin and how, you tap it and it blows up, and Alfred Nobel figured out a way to stabilize it by mixing it with weird stuff. Well, they found out years later that the reason it was unstable was it wasn't only nitroglycerin. There was an impurity that they didn't know was there. It was actually left over from the process. It was like an acid or something that shouldn't have been there. And if they had a better process and made clean nitroglycerin, it would have been fine. So it's just an interesting little quirk there. But you couldn't have those westerns without the nitroglycerin blowing up all the time. Testing, all right. So this is the Mars Polar Lander, and let's see what happened to this one here. Oh no, I'm sorry. That was the one that failed prematurely. Sorry about that. I got them mixed up. Oh, I'll go back. This was the one where the sensors in the legs inadvertently thought that the device had landed and turned off the motors. The Mars Mariner 1, it failed when they were documenting software, moving things around, and let's see. Oh, here it is, I think. There it is. It's down at the bottom. What they did was the code, the computer code said R bar, all right, which is on the right. Somebody wrote down R without the bar. And that, of course, completely changed the meaning of the computer program, and the thing failed. Just again, somebody not checking or paying attention, or somebody who wasn't aware of the details of programming a computer. Sorry about that. Operator error. Okay, so something like half of, if you look at a particular environment, like airplanes or chemical plants or something, supposedly it's about 50% of the problems of the really bad errors or operator error. I don't know. It depends so much on the environment, but and it depends who's telling the story too, of course. But anyway, it certainly is a big problem. This is a wonderful YouTube if you can find it. I mean, it's terrible, but it's wonderful. This was back in the 60s or something like this, and these two pilots, there were two back then. I think there were two pilots, a navigator, and maybe there were at least three. Maybe there was a fourth. I don't remember. And they're flying along, and they put the landing gear down, and there are three levers: one for the left gear, one for the right gear, and one for the nose landing gear. Well, each one has a pilot light. Well, the pilot lights on the left and right indicated that the landing gear was down. The pilot light on the nose didn't. Okay. Well, of course, that's a big problem. And they tried to have the traffic control person look at it visually by flying by, but he couldn't tell if it was locked. So they didn't know what was going on, because was the light bulb bad, or the switch bad, or was the landing gear really bad? And they actually sent a guy down. It's called a hellhole. I have a picture of it, which is under the deck beneath the cockpit. And this guy was trying to crawl around. It's like 20 below zero, and he's trying to crawl around, trying to peek at the landing gear. He couldn't tell. They came back up. Then they tried to disassemble the control panel, because they had a light bulb that might work, and the plane crashed. All right. What happened was they bumped the autopilot, turned it off inadvertently, And of course, the autopilot would keep them above terrain, but it didn't, and the plane crashed. I mean, it was a terrible story. But I mean, these people were actually arguing about this stupid light bulb, and they forgot all about the plane. And that's, you know, a great example of distraction. So, and you know, that brings up the question about these indicators. So another problem going back at 3 Mile Island was that you threw the switch to open that mysterious valve, and the light bulb was supposed to tell you that the switch was, you know, like green if it was open and red if it was closed. Well, the problem was the light bulb just told you the position of the switch, not the position of the valve. I mean, think about that. I mean, and that's how they all work, you know, and it's just, you know, I mean, you know. So anyways, this is a terrible story, but it's, you know, it's human nature, I guess. Ergonomic equipment design, back to 3 Mile Island. This panel is 60 feet long and has 1,600 controls, most of which are designed or placed in relatively random locations. And when all this was going on, they had 70 people in the control room. I mean, can you imagine? It's just, and then, you know, you had like these tags I mentioned, which covered up controls, and I mean, it's just, you know. Then there was a famous story where they were doing just maintenance work on a plant, and somebody wanted to check a conduit that had a bunch of cables in it. They wanted to check it to see if there were leaks, if the conduit was sealed. So he used a candle, and he started the cables on fire, and, you know, millions of dollars worth of damage. So, but they learned a lot in the whole science of ergonomics and psychology and how people react through 3 Mile Island. There was a lot to learn. The control panel was completely redesigned, obviously. And if you think about it now, if you look at like airplane cockpits, everything now is screens. So it's not little levers and stuff. You know, you can do a much better job of human factors engineering if you have the ability to, you know, put block diagrams on screens and not have physical switches. Operator training and instruction, all right? There's actually a book on the history of torpedoes and all the problems. So in 1939, the Germans, of course, they were in war already. The U.S. was, you know, caught, you know, with their pants down. They had to start, you know, making armaments and all that. So they started working on torpedoes. Long story short, they didn't work until the end of 1942. They had terrible problems. It was okay because the Germans didn't work either. In fact, Winston Churchill was on a, you know, surreptitiously, secretly, he was taking a freighter, I don't know, it was across the Atlantic or somewhere in 1939, and the Germans knew he was on that boat and fired a bunch of torpedoes. Theirs didn't work either. And that really changed the course of the war, as you can imagine. Torpedoes were a problem. The Japanese had wonderful torpedoes. They were called Long Lance. And they had twice the warhead size, and they were incredibly reliable. The U.S., about 90% of the torpedoes didn't work. And, you know, they'd bounce off the ships, they would explode prematurely, and in any case, if a torpedo misfired, it would give away the position of the torpedo because there was a wake or a premature explosion. And the torpedo, the submarine, you know, sailors, I mean, they were just a revolt. I mean, they were going crazy. And now you come to the bureaucracy. The same bureaucracy was in Nazi Germany, the same idea. The Germans, of course, were very, very strict in their organizations and their procedures and all that, and they wouldn't listen to the sailors. But the U.S. wouldn't either. They couldn't persuade the sailors would come back, you know, having fired, you know, 10 or 20 torpedoes, and none of them went off. And of course, the management blamed the sailors for that. And to give you an idea how crazy this was, with all these problems with the torpedoes, with technical problems, they also forgot to send operating manuals out. So nobody even knew how to operate them. I mean, these were complicated. You know, you had to set the depth and all this kind of stuff, and it was just chaos. And, you know, I mean, they were blowing up right outside the submarines, and terrible. Very interesting, though, you know, when you think, I'm sure you've all thought about torpedoes. But if you, depending on the kind of ship you're after, you really want the torpedo to blow up under the ship. You don't want it to just hit the side of the ship, because it's very easy, and they did. They put these bulges, and sometimes you see those on ships, these bulges that would prevent the torpedo from penetrating. And so how would you do that? How would you explode the torpedo when it got close? Well, they had this great idea. They would reference the Earth's magnetic field. And they would have a magnetometer in this torpedo, and when it sensed that the Earth's magnetic field had been disturbed, then it would set off the explosion. Well, of course, that's great because they tested it in the northern hemisphere, but when we went to the southern hemisphere, it was backwards. And the signal was negative. It should have been positive, but of course it didn't go off. And they had to map the magnetic field of the Earth, and it was just terrible. But they were desperate, so they tried. I don't even know if they ever got that to work. They probably came up with rather than a passive scheme like that, an active, radio scheme or something, so they could fire the torpedo. A lot of them were just contacts, when it bumped into the ship. But of course, they couldn't get it under the ship. The other problem was they never got the depth control to work properly. One of the reasons was they had a vent to measure the water pressure, forgetting, of course, about good old Bernoulli's equation, that depending on how fast the torpedo was going, it created a vacuum in this little hole and totally screwed up the measurement. And there's all kinds of problems. A lot of them just leaked. They had to sit in the torpedo tube for maybe 15 minutes, to get ready to launch, and by then they were all leaking salt water. And so it was really terrible. I mean, it was, not funny terrible, but it was really tragic. I mean, the number of duds were just unbelievable. And this is a bigger problem actually in the Pacific, because the distances involved and everything. Submarines were really important. Interpersonal conflict. Okay, this is a great one. Malcolm Gladwell, is that his name? Yeah, you've probably read some of his stuff. He talked about this. Having to do with cultural differences. And in Korea, the culture, assumed that there was a very, very strict division based on authority and position and hierarchy. So you had a captain and a co-captain, and the co-captain would say to the captain, "Sir, the engine's on fire," and the captain refused to listen to him. And they were having terrible crashes because they would have this silence, and they basically only had one person driving the plane, and the co-pilot had certain responsibilities, but the captain didn't pay any attention to him because he was a lower status position. So when they figured this out, their reliability obviously got much, much better. But that, just shows you how, psychologists go to work for airplane companies, and sociologists for that matter. So these systems are built of components. We've been talking about the system problems, how one component relates to another, but much like the incidents, the little gadget, the little, tool you buy to take home, these individual components obviously can fail and start a sequence. So some examples, of that. I hit my button again. No, that's at the end. Very sensitive mouse here. Okay, design and or manufacturing errors. This is one of mine. I'll take credit for this. If you go to most airports, you see a sign that is curved like this. And this is made by a company here in Cleveland called LumaCurve, and they make them all. And they've been making for many years. But they needed some electronics because of these weird wiring situations in airports. It just has to do with the fact they have to be dimmed, and that there's hundreds of, many, many miles of wiring and all that. So these lights, off on one side, had a power supply, which I designed for them. And the environment is terrible. These signs are not really sealed. But they're actually sort of expendable because they keep getting hit by the exhaust from jets and getting blown over and stuff. So they're sort of built to be repaired. But so they're not sealed up, and the power supply had to be sealed up for moisture and such. So I just took a box, like this big, and the printed circuit board, this is side view down there, and the printed circuit board had electronic components soldered to it, like you typically see. One of them was a power transistor, which I've shown in a larger view down at the bottom, and that was perched on the circuit board and soldered underneath the circuit board. This circuit board only had copper foil on one side. That's the way it was done then. And then it was filled up with epoxy. And they worked fine for a while, and then they started failing. And so, obviously we had to get to the bottom of that. And what was happening was that it turned out to be temperature cycling. And the thing was filled with epoxy, so there was obviously epoxy between the body of this part, this part, and the circuit board, which was down here. You can see it from up here. So there was epoxy all over, but there was also epoxy there. So the coefficient of expansion of plastics and epoxy is much greater over temperature than that of metal. Metal doesn't change much, but this epoxy was getting bigger and smaller, when the thing was in the hot sun and what have you. And so eventually, this soldered connection on every one of these things broke. The part got pushed down, peeled off the copper, and it broke away from the board. And it happened to every single one. And, the question is, what is the responsibility? Well, we blew it. We tested these things, but we tested them at very high temperature and very low temperature. It's actually a little bit cumbersome to test things over drastic changes in temperature, and we didn't do that. The fix was relatively easy. We put a little S-shaped kink in the lead, so now the part could move up and down. We used a softer epoxy, and we used a double-sided circuit board, so we could solder it both on the top and on the bottom. And that made like a rivet, so it was much more secure. So fixed that problem and certainly learned something in the process. But that was another one of mine. There were many. Imperfect component testing and qualification. Apollo 13, that was relatively recently. Everybody knows that story. What was curious about this is that they tested it, but the testing destroyed the product. They tested it, and for reasons, probably economic reasons, to speed things up, they had this was an oxygen tank with a heater in it. Because in order to get the oxygen, it was probably liquid oxygen, and they would heat it to get the oxygen to flow, so they didn't need a pump or anything. So in testing, they, for whatever reason, I said might have been just to speed it up, they tested this thing at 60 volts, whereas in operation, it only ran on 24 volts, so the heater was only designed to operate on 24 volts. So anyways, they tested it, and in the process destroyed it, but never knew it because the test was over. So it was not working. The thermostat was faulty, and it was basically welded shut. And then they went ahead and installed it without testing it again. So somewhere along the line, somebody made a pretty grievous error. So that was the story. There was not really any consecutive, linkage there. It just blew up, and from then on, they were, scrambling to make it back. Misapplication. This seems to happen all the time. These tanks buckle, petroleum tanks or chemical tanks, and it's an example of sort of consecutive or simultaneous failure where somebody isn't paying attention. So they want to pump something out of the tank and forget to open the valve to vent it. So it just makes a huge vacuum tank and it collapses. And this seems to happen all the time. And if you go online, there's picture after picture of these collapsed tanks. And I'm sure that it could be a huge problem, if it's flammable or something like that. So that could be training, it could be procedure, don't know. Obviously, overuse is a problem, things wear out, but maintenance is really a problem, and that's what happened in Bhopal, which you probably remember. I think 5,000 people died, and they're still dying. It's a terrible, terrible, tragedy which Union Carbide never has really taken responsibility for. And so, in this case here, and this has been, pretty well understood and documented, but I have to read it to get it right. There was a tank filled with this very, very nasty methyl isocyanate. The methyl isocyanate, right. So it sounds bad, and it is. And unfortunately, it doesn't like it to be mixed with water, but there was a faulty valve. So that's maintenance issue number one. There was a faulty valve which allowed water to get into this tank. So there was water in like an adjacent process, and somehow it got piped into this tank. So an exothermic reaction resulted. They knew about that at least, but they never figured that water would make its way into this huge tank. So the pressure built up, and then there was a vent. They always have a pressure cooker, and your hot water tank has an overpressure relief valve, and they had one too, but they had turned it off 3 weeks ago. Maybe it had been leaking. All right, so that's another problem. Then they had a system to keep the tank cool, because if you have an exothermic reaction and you can keep it cool, the reaction will cease or never start. But they had removed the coolant from that refrigeration system because they needed it someplace else. They were some other refrigeration unit, so there was no refrigeration available. Then the last system is to simply flare it off. And you see these flares, waste gas, and they have them in the flats in Cleveland. And the idea is you don't want to use the flare because you're wasting obviously material, but they do put them in as sort of a last ditch effort. This one had been inoperable for 3 months. Okay, so here is so anyways, 2 hours after the problem was noticed, a safety valve blew up and finally released the pressure, into the environment. So, I mean, this is a classic example of, frankly, it wasn't the operators in India, it was the people in the U.S. and Union Carbide who were just asleep. They just didn't want to fund or pay attention or anything. And so, I mean, I don't know, they paid something, but again, they still haven't cleaned up the contamination from this 40 or 50 years later. So it is really, really terrible. It's become a bit of a tourist site, by the way, though. Just like Chernobyl, which I would like to visit, actually. All right. Okay, mechanical or stresses exceeding design parameters. So whenever you have a design, you sit down and you figure out, all right, not only what does it have to do, but what does it have to resist, or what does it have to work over? What is the maximum temperature? If something has to work on in the engine of a car, it's got to work up to like 250 degrees F. If it has to work inside the car, it has to work like to 185 degrees F. And there are all these requirements, and they're specified by, like the Society of Automotive Engineers has temperature requirements. And so airplanes have an incredible series of limitations and parameters. How fast you should try to have the airplane rise, without stressing the wings, or how your speed of landing. Obviously, how high you should go, because if you run out of lift because the air gets so thin, bad things are going to happen. So there was a Pinnacle Airlines. They're gone, obviously. This slide. And they had a ferry move an airplane from one airport to another. So the pilots were flying an empty plane, and they decided that try some horseplay. And they had this informal little group that was probably thought of over too many drinks, where the pilots in this airline all tried to join the 410 Club, was where you flew your plane at 41,000 feet, which was the limit of this particular type of airplane. And so these guys were out there joking around, and and they had all the cockpit recording, and they brought it up to that speed, but they weren't good enough. They didn't know what they were doing. So the airplane stalled, and then it fluttered down, and they couldn't restart the engines because they weren't paying attention to another requirement, which was to keep the engines turning so it doesn't lock up with ice. So both engines locked up with ice. They couldn't restart. They tried what's called a manual restart, but they hadn't read the book, and the airplane crashed. So no people were on there, of course, and they probably wouldn't have pulled this stunt if there had been people, but they paid the price. So that was another well-known story. Unanticipated events. Okay, these might be called acts of God or something, or it'll never happen here. And so, let's see here. Oh, no, that wasn't it. I left out one link, so I got to find it here. Resort to paper when all else fails. See. Oh yeah, the Ocean Ranger. If you remember that, that was quite a, it was a tragedy that went on for a few days, and quite a few people died. What happened was these large oil rigs. I mean, there's all different kinds. Some of them sit on the ground. But some of them actually float, but they have these long legs, basically, which they fill with more or less water to stabilize these things. And they have all kinds of sensors and pumps and obviously fancy control systems to keep the thing level and keep it, in location, too. So this is one of the most advanced ones. And, I mean, I don't no idea what it cost, but I'm sure it cost, upwards of, hundreds of millions of dollars. And everything was fine, and a big storm came, and the computer room was located up on the deck someplace where it should never have been subjected to waves. I mean, that was in the specification. And it had a window. Well, a big wave came, smashed through the window, and of course all the controls were gone, and so they couldn't stabilize the thing, and basically it sank, and lots of people died. And so there was an example of to them it was unexpected. That never should have happened, but it did happen. So you have to be very, very careful in defining these things and saying that's never going to happen. And of course the reliable products, the reliable systems are the ones where they've stretched the parameters to include every conceivable thing. But then again, you have the act of God. Are you designed to survive being hit by a meteor or something? Well, it happened here recently. And then 9/11 was obviously a catastrophe. And it was interesting because the buildings were actually designed to survive being struck by a modern jet aircraft, which is amazing that they would do that. But then extending the thinking, they figured that the plane would not be carrying much fuel because they figured if it was going to crash, it would be landing. Why they didn't think it might crash when it was taking off, I don't understand. But for some reason, maybe the location of the airports in New York or something, they designed it to hopefully withstand a crash from an airplane that was not loaded with fuel, which is, like sort of going halfway, but that's the way it was. So, back to the beginning here. So, what do you do? Well, this is obviously the shortest part of this talk because it's pretty obvious, okay? This concept of separation of components. You don't have the same power supply operate the light that's controlling the valve, so you try to split these things up. And you try to simplify it. As I always would tell my students, the most reliable component is the one you don't use. All right, so throwing in extra stuff, it's a very, very fine line. Yes, you want to have redundancy, but having those tend to be parallel things that take over if something goes wrong. So in an airplane, everything now is run by hydraulics, but there are actually two separate hydraulic systems with check valves because they found a number of accidents occurred where there was structural damage to a plane and the lines broke, and all the hydraulic fluid leaked out. They couldn't control the planes, the surfaces. So now they have two systems, but of course they used to have two systems and ran the pipes close together, which sort of defeated the purpose. Now they have two systems, but they keep the pipes separated, and the same thing with electrical cables. So there are obviously a lot of things you can do to reduce complexity and fix the for example redundancy, backup systems. For example, I was always fascinated by, in the process of designing those landing lights, they have backup power for landing lights. I'm not talking about the signs that I made that just told the airplane what gate to go to, but the actual lights aligning the runway. You don't want those to turn off, when the plane is landing. So what they have is they have get power from what is it called, the illuminating company, one utility, but they also get power from another utility, and they have a switch. But then they have two generators, diesel generators, and the generators are in different buildings. All right, that makes perfect sense. So far it makes sense. But the fascinating question is, when do they turn on those generators? They turn them on when it gets cloudy or windy. I think that's brilliant, because they don't want to say, oh, we got to turn on the generator, the plane's landing, and find it doesn't work. So they have all the utilities are still operating. They switch over to the generators, operate on the generators, and use the utilities for backup, because that is the ultimate reliable configuration. I was really fascinated to learn that. I thought that was neat. So, and so redundancies, obviously it's hard to do, because in the process of putting in redundancy, you are creating some complexity. Okay. This concept of a hot swap, maybe you've heard of that with computer systems and stuff. You can unplug one thing and plug in something else without losing it. It's very, very hard to do. So you keep both of them operating. That's redundant parallel operation, but it is very, very tricky. Then event analysis and feedback. Accidents are going to happen. And if you can analyze the root cause, doing a better job than I've done here, obviously you can try to fix it. And that's, you've got to assume that, these things are going to happen. Don't let them happen again. That's about the best you can do. And you can do all the modeling in the world, but things are still going to happen. That analysis of root cause reminds me of the old SPC, where the Japanese, with American help, learned that by analyzing failures, you go back to the beginning of your process and fix it. All right, it was feedback, and typically, like the American auto plants, if a car didn't work at the end of the assembly line, they would just sell to somebody, and that was it. But the Japanese learned that this statistical quality control was very, very valuable, and you can do the same thing by analyzing failures. And then this gets to a whole other lecture you could have, which has to do with disclosure and honesty and whistleblowers and all that. I mean, that's a really, really interesting topic, because if, say, you're an engineer and your company is making something, and maybe it's safety or health related, and you have a problem, well, of course, everybody in this room says, wow, I noticed that I'm testing this thing improperly, I better inform management. It's not that easy, because they pay you, and that's your job. You've worked there for 30 years, and you made the mistake. It's a little bit dicey. So this whole whistleblower thing and laws to protect them, that's a very interesting discussion. It's not so easy. The best example, by the way, how are we doing time-wise?
You're doing great.
Okay. Does anybody remember the infamous keychain problem with cars? I forgot. It was General Motors. Right. If your keychain was too heavy, so if you hung like a skull and crossbones on your keychain, and you're driving along, on a twisty road or something, the weight of the keychain would cause the ignition switch, back when they had keys, to switch from like on to off. So your car would turn off. Sometimes the steering wheel would lock, and your airbags would turn off, the engine would turn off, the power brakes didn't work, the power steering didn't work, and I think like 100 people died over the course of a couple of years. And this whole investigation was incredibly complicated. The switch had a detent. And now there are actually probably SAE requirements that say that, a certain amount of force it takes to turn the switch, the key switch, from one position to another. They didn't have that then, so they had, a couple of engineers in the back room setting the standard, and it just got all messed up. Somebody changed the spring for whatever reason and made the detent too weak, and so this problem started to happen. Then somebody else changed the spring back. Nobody recorded when any of these changes occurred. In a good business, everything, all changes are recorded with change orders and date of implementation, and the important parts are recorded as they go down the assembly line. They didn't do any of that, so when it came to recall the cars, they had to recall like 8 million cars, even though a relatively small number of them had the problem. They just didn't know which cars had the problem. So it was a very, very catastrophic. 8.2 million cars they recall. It was catastrophic. They were fined, I think, $28,000 or something. But anyway, that's a good example where documentation and control comes in. But that engine, I'm not exactly sure. I don't think that engineer ever reported it. 15 engineers lost their job. I know that, or inspectors. But again, it's the whole question. If somebody had, stepped up and said, we're having a problem with this 10-cent spring, then maybe it would have been taken care of. So that's where the culture of transparency. And then you need this overall organizational commitment. You have to say, look, we're going to do things right. We're going to institute these procedures, and you're not going to shortcut them, and you're not going to lie about them. And the procedures are going to be formal and written, and there has to be a process. So even the simplest thing, if it's related, if it has a function that there's a lot of liability for damages or health or something like that, it has to be very, very properly and carefully made. And of course, when you buy these little gadgets like from Amazon, like a kitchen, egg timer, a digital timer or something. I don't know if they ever test them. I really don't know. I mean, I don't think they bother. I mean, these things are just so incredibly inexpensive. So I don't know. When I was building, things, electronics, and one of my customers would get a quote from a vendor in China. They priced the whole product at less than I could buy the parts for. And you just can't compete. You just can't do a good job under those circumstances. So, but adherence to the process, to the specifications, review, the documentation, you have to enforce that. And that's, nobody likes to be the bad guy, but that's what you have to do to get this stuff to work properly. Let's see, I have something else here. I'll call out another one of my problems. This was definitely an accident because I almost died. I'm not sure I've told this to my wife in a while. But back on Murray Hill, we would solder circuit boards. And the problem, I mean, it's still a problem, but you would solder circuit boards with rosin, the same stuff that comes out of a tree. And you had to clean the circuit boards. And there's all these schemes to clean them and stuff, but a quick way and a reliable way was to use a vapor degreaser. So these are, fancy machines, but then there was our machine, which was a 55-gallon drum, and it had a garden hose wrapped around the top, and it had an electric heater down at the bottom, and you would pour in trichloroethylene, which has now been banned, and you'd have, 5 gallons of this nasty solvent down at the bottom, and these electric heater coils would make it boil, which is pretty bad when you think about it. And then there was a basket, and in the basket you'd put the stuff you wanted to clean, and the vapors would come up and they would dissolve the stuff you wanted to get rid of, which would drip back down into the machine, and the vapors would keep rising, but hopefully the garden hose, the cold water, would cause the stuff to condense and fall back into the barrel. The problem with this thing is there was no way to clean it. There was no drain, you couldn't empty it. So somebody, mainly me, had to get in there with like a scoop and scoop out this hardened goop at the bottom. So I was alone, because I was working all hours. And this thing was in the basement of the Murray Hill Market, which is where my company was. And I had a scoop, and I leaned over, forgetting there was no oxygen in that barrel. I mean, the machine was turned off, of course, it was cool, but it was all trichloroethylene vapor and no oxygen. So I fainted, but fortunately I fainted and fell outside the barrel rather than inside the barrel. So that, you're laughing now. But eventually I got rid of all the solvents in the company. No solvents were allowed. So. But anyway, that was the story. If we have a minute, another one that is pretty contemporary, which I think is just frightening. If you've used the CPAP machine, you'll know there's been a terrible recall of CPAP machines, ones made by Philips. And this shows you the value of, when you're 10 years old, taking apart toys or tinkering, or just being someplace where you see how things are put together and what works and what doesn't work. And if you ever taken apart maybe like an old speaker cabinet, it has foam in it, foam rubber. And you probably know, especially this black stuff, it decays and it just crumbles and it goes all over the place. Semiconductors used to be shipped in this stuff, and the stuff was so nasty that you'd open up the container and your transistor was laying there and it'd be just covered with this disgusting black powder. And anyways, that foam, maybe not exactly the same kind, was in these CPAP machines. And if somebody told me that there was some kind of rubber foam or urethane foam or something in a machine that I was going to be breathing with, oh my God, I mean, because this stuff, it just deteriorates. And it's packing material. And they used some kind of garbage foam, which after a couple of years deteriorated, and so everybody was breathing in this decaying, foam, and it was just terrible. I mean, it's in your lungs, who knows what happens to it. So there's an example of somebody should have said, hey, I once restored my old car, and I looked at the foam in the dorms, and it was all cruddy. Maybe we shouldn't use this stuff. So they have a big problem, that company. So, but anyway, another example of that is the Challenger, where the temperature was too cold, and they were all arguing about this and that. But one of the theories is the theory of diversity. If you know a little bit about the space program down in Alabama, Louisiana, Texas, these engineers generally went to one of 2 or 3 colleges. Texas A&M, I don't know what they were, but they're these big schools and they have big football teams. And all the engineers go there. And you have to imagine that they pretty much learned the same stuff, and maybe they learned to think about the same way. And when you got all these people in the room trying to decide if this thing should take off, I think one of the problems was you didn't have a diverse, collaborative group, and they all sort of went with the flow, because that's what they did on their football teams or something. So I don't know. That's my personal theory. I mean, there was obviously the problem that management said you got to make this thing work, and you're going to do it. And of course, it was too cold. But I just think that there was this opinion back there of a little bit of lack of diverging opinions that may have led to some of that problem. So, all right, that's that. Oh, one last thing here. Okay, let me finish up, and then lots of questions. You've probably read about Admiral Rickover. He was like 5'3" or something, and ran the Navy for a while. I mean, he was a real character. He was tough as nails. And he ran the submarine corps, so of course safety was his big thing, and they were nuclear submarines. So it's just interesting to read his rules for how management interacts regarding safety. And I don't know, it's pretty. I think it's something pretty good that you could go by if you ever are running a submarine. The books I've used for this thing are more or less available. And those are the books there. So, and you know, they're actually pretty interesting, and they analyze more or less a lot of these catastrophes, as do the YouTube videos too, where they have pilots talking about what went wrong. So, question? Yes, sir.
I was going to ask you if you were familiar with the Ashtabula tricks.
Oh yeah, in like 1880 or something. Yeah, yeah.
It would be fascinating to take all of your checklist of all the
Yeah.
things that could go wrong and just break that whole thing down and say, this is where this failed and this is
Yeah.
where this failed. And this is
You know, that is an interesting story. That goes back to one of the New York financiers, and somebody tried to murder him because he designed the thing, and it's quite a story. There was this huge, obviously wooden trestle that a railroad ran over I guess the valley of the Ashtabula River, and it collapsed, and you know, quite dramatically. And I guess you can still see like the abutment and some of the consequences. But the story, the aftermath, and all that was pretty interesting. So.
Yeah, it was a tragic thing, but just the whole story of the engineering and how the engineering got compromised and then compromised again, and the zoning guy got.
Oh, I didn't know all of that. I just knew the aftermath, the architect or the engineer, the financier. There was all kinds of drama.
It would be an interesting thing to take your kind of like
right.
boxes and just apply them to that whole story and say, this is where this failed and this is where this failed.
Again, the sequential nature of it. Now, of course, a lot of this stuff is fairly well documented. And back then, I'm not so sure.
So Professor Sears.
Yeah, that's right.
Is this taught in engineering school?
You know, that's interesting. If it is, it's done sort of asynchronously. I think the really good example is this little product of mine, which was done by the book. You know, I mean, if you simulated that on the best computer system in the world, it would work fine. But somebody has to be able to have the experience enough to know that this is what it's going to face in the real world.
But these lessons that you compiled here, it just seems like that should be part of engineering.
Yeah,
an engineer, we all know.
Yeah, that's right. Yeah, I have talked about it once. There was some kind of seminar or something like that. But yeah, by the way, I might take this and do it, like somewhere again. And so this is a trial. So.
Yeah. On a positive note, after Bhopal and the similar tragedy in Charleston, West Virginia, these chemical plants are in valleys because they're by rivers.
Yes,
and of course you had an inversion, and thousands of people died. But after that happened, the chemical industry started saying, we're in trouble, and we need to do something about that. I'm on a citizens advisory panel for Lubrizol.
Oh, really? Oh, okay.
And 4 times a year they gather all these citizens and they tell us about what they're doing to prevent some of these things. And the last 2 points that you made on your final slide, what they should be doing. It's very interesting how they've incorporated that into their everyday operations. For example, they will reward workers if they can find mistakes.
Okay. Yeah. Okay.
On a daily basis.
That's back to that whole whistleblowing question. Don't bury it. Yeah.
Yeah, and so this is it's not a negative thing. It's a positive.
Right.
They want to find these mistakes, and then on top of that, the supervisors, managers, even the middle managers, they have been instructed. They have to tell safety things, so many safety things every week.
Oh, really?
And it's marked down, and they're evaluated for that. So they're taking some of these things.
It's also interesting, though, does this translate to, say, just quality? In other words, safety is one thing. Do these same people report problems with quality and
Yeah, as a
it's
matter of fact, the
complicated.
people that are in charge of it, it's safety and quality control.
Okay,
That's the
yeah,
office
okay,
of
well,
it.
that
So,
makes
you know,
sense.
it's sitting there,
No
and
idea,
I was
but-
a high school teacher
Yeah,
that they
okay.
invited to come to this thing.
Okay.
And I've been on it
Yeah.
for 28 years now.
Really?
It's interesting to see how they have developed this.
It's very interesting to the program. First of all, in the 60s, the safety of flying is like, I don't know the numbers, but 10% of the accidents that they had back in the 50s and 60s. And one of the reasons was that the way it worked before, if say you were a pilot or an airline mechanic or something, you didn't report a safety failure or a particular equipment problem. One, your boss didn't want you to report it, and two, the flight might not take off and you'd be penalized. So now the FAA has these strict rules that you to turn it around, and the way they did that is by saying they will not fine or punish the airlines or anybody for reporting a problem like that. It makes perfect sense, but not until somebody does it.
That's
Yeah, so that made a huge, and the checklist too. You've probably heard about that. Right, where somebody went around to hospitals and saw how they did surgery, and the guy said, well, why don't pilots have checklists, when they take off? Pardon?
Atul Gawande wrote Check the Checklist
Okay.
Manifesto.
Yeah, oh, okay,
And they
yeah.
go through all sorts of information about checklists.
Uh-huh.
It's really a good book.
Did it start by talking to surgeons or in hospitals?
Yeah, he was offered to be put in, he's a surgeon at,
Okay, yeah, that's what I heard, that's where it came
Harvard Med. He
from.
was asked to be put, somebody asked him about, what do you do the World Health Organization Safe Surgical Initiative?
Oh, okay, yeah.
And he said, well, is there an office? Is there pay? Is there, no. He said, well, I don't know. I guess I called the wrong guy.
Yeah.
Thank you. And then he got, he
Oh,
called back
about
the
it,
next day
yeah,
to do it.
Yeah.
So he started with the construction company out the window. And they did a lot of stuff with surgical suites and all the stuff you see now with names, and introductions, and a lot of formalized sort of cockpit control procedures.
Right, yeah.
And it's a really good book on that subject.
Huh.
The safety thing, I think Alcoa, that's a really good story.
Paul O'Neill.
Yeah, Paul O'Neill, who was Treasury Secretary, I guess, later. Yeah, but when he came in, a couple guys had been killed in their mills. And he said safety is going to be the only thing, that is the number one thing across the board. Complete safety everywhere in the organization. And all these guys were like, well, okay, let's see if he really means it, and he really meant it. So they said, okay, that's what we'll do. And what happened is that consciousness drove really good procedures and checking and all sorts of good behaviors.
Yeah, it took a while to catch on because management eventually realized that it would actually save them money. Now,
And
to
increased
one,
profitability.
and for them to think that their plants blowing up was not causing them money is hard to believe. But the other thing that they used to do, they used to have these big signs that said "days lost due to injury." You still see those. And, you see those in movies of the unions in the 30s and stuff.
There's one on the shoreway that's
Still, yeah, and they would use that for like an indicator of like overall quality and performance. But no, they were just focusing on people, just simple things. They weren't focusing on the big picture that these tanks were blowing up. So they decided that's not a good predicate for overall plant safety. So they learned a lot.
So wasn't the name Pinnacle Airlines enough?
Yeah, right. Yeah.
Not to mention that
Right.
the CEO previously was at Icarus Airlines.
Right, or Nader Airlines. Yeah, very good. Yeah. But
Larry, that comment you made about all of the engineers being from the same school, it piqued my curiosity about what do you think? A number of years ago, there were some efforts to standardize high school education in Ohio to really focus on mathematics and science, and they kind of pitched arts and music and things like that out the window. And I'm just curious if you cared to expand on engineers coming from different backgrounds or different schools.
it's funny because there's a lot of, I'm not sure if politics is the right word, but in the I mean, I started at Case, you know, what, 60 years ago or something. And it's interesting just to see the changes sort of in the philosophies I've seen. When I arrived in the basement of Bingham Building, there was a steam engine. And there was all this, you know, pumping equipment. I mean, just like the stuff that looked like at a museum from the 1880s. And then one day it was gone. And I said, where did it go? And they said, well, we sent it all to Cleveland State. So I thought that was pretty telling. And then at a completely different level, years later, I came back for some reason, and they said they had a motors lab. And I said, oh, motors, I like motors, you know, and I envisioned something reminiscent of the old stuff in the building with a bunch of motors, you know, and you get oil in them and they make noise. But no, I walked in this room and it had computers, and there were no motors. They were computers modeling motors. And that's just too far removed, you know, it just wasn't the real thing. And so I thought that was interesting to see how things change, but not necessarily for the better, you know. So, I mean, there's a tremendous gap between the theory and getting something to work. You know, I've just been thinking about it and talking to Sally lately. You could teach all the theory, all right, all the equations, or, you know, a circuit or a system or something, and then you could go into the lab where you do experiments, or you put things together. It's sort of packaged stuff, you know, tab A into slot B, and you're basically recreating the theory, which is fine. It supports it. You learn a few things. But then you get a job, and you're assigned, say, to build that little Monsanto timer, and then, you know, the engineer would say, you know, where do I go? Where do I start? You know, it's very different. It's far removed. There's a chasm there, I think, between the theory, the training, and then ultimately being an effective engineer. And well, you know, you look at some of these disasters, and of course, you see the consequences. I mean, I was just flabbergasted when I read about that CPAP machine. That was just stunning and really gross when you think about it. So, but any other questions? Mm-hmm. Okay. Case does have an ethics person now. It's mostly military ethics or political ethics. So they do have somebody who thinks about these things. So that's good. So, all right. Well, thank you very much.
Please give it up for Larry Sears.
Thank you.
Thank you so very much. This was fascinating. And thanks for agreeing to do it.
All
and
right.
I hope you will be a source of lots of great suggestions for speakers.
All right, and
Right, Larry?
yes, and thank you for letting me practice on you.
So we will be meeting at our standard time next month. We presume we're meeting here, but pay attention to the emails. We are going to be learning all about plant carnivory, which should be kind of cool.
The speaker was right here.
Oh, really?
The speaker, yeah.
Oh, so our speaker's here. But particularly when carnivorous plants are being raised in the dormitories of Case Western Reserve. It should be interesting. It should be a lot of fun. So, and there's a chance we might be at a different venue, but just pay attention to that. We've got some conflicting information from Jolly Tree. Thanks for coming out tonight, guys, and we'll see you next week.